Welcome to the 16th lecture of the course on mechanics of machining. In the previous lecture, we discussed about turning process, and in this lecture, we will discuss about milling and drilling process. So, machining by milling is different from shaping and turning in the sense that material in milling is removed by a rotatory cutting tool with a large number of cutting edges rotating about a fixed axis. So, there is a cutter in which there are number of teeth. The axis of rotation of cutting tool is perpendicular to the direction of feed, and milling operation requires a milling machine, fixture, workpiece and a milling cutter. It is one of the most versatile machining operation for producing flat surfaces, curved surfaces. Mostly we can machine the rectangular jobs also. The feed motion is provided to the workpiece and the cutting speed is provided to the cutter. In the turning operation, the workpiece rotates, but here the workpiece is stationary relative to the rotating cutter. Milling process provides intermittent cutting with each tooth producing chips of variable thickness. This is essential difference between turning and shaping and milling, because in turning and shaping there is a continuous chip production, but here there is a intermittent cutting. So, we can classify milling operation in various ways. One is depending on the machine. So, one is horizontal or plane or peripheral milling. In this, cutter axis is horizontal. It is further divided into two groups depending upon the relative direction of cutting and feed motion. One is called up milling. In the up milling, cutting and feed motions are in opposite direction, that is up milling, and in down milling, cutting and feed motions are in the same direction. Then we have vertical milling and also end milling. In these processes, cutter axis is vertical or perpendicular to the work surface, and it can be classified into slot milling if we want to make a slot. It can be face milling if we just want to do facing of the surface, we want to remove, just like in the turning operation we do facing also by a cutting tool. Similarly, here in the face milling also we can do facing, we can make the plane surface on the top. Then T-slot milling, in which if we want to make one T-slot, you know what is a T-slot? No, it is like this, and it is in which you can fit a T-bolt. So, this type of slot is generally made. You might have seen a milling machine table in which these type of T-slots are already made, and various other places like in a planer also sometimes. So, T-slot is used for fastening. There will be a T-bolt which will have this type of head. It can be slit inside the T-slot. So, T-slot milling is also there, which makes T-slot. Then let us discuss about down milling and up milling. You see that in this figure there is a plane milling process shown. So, part A is showing up milling, in which workpiece is moving in this direction from left to right and the cutter is rotating like this. So, therefore, peripheral speed of the cutter with respect to workpiece in opposite direction to that workpiece, actually this one. So, that is what is happening, and in the down milling, workpiece is moving in this direction, peripheral speed of the cutter is also in the same direction. So, both are essentially moving in the same direction and it is going like this. See here, in this case, O initially it was, this is the center of the workpiece O, and this has gone O prime, that means relative to workpiece, you can say this has moved from here to here, okay, relative to workpiece, otherwise work. Similarly, in this case, it is center is here and then it goes there. So, that means up milling and down milling, these processes have been shown here. In down milling, the chip thickness is maximum at the start of the cut and drops to 0 value at the end of cut. So, in the down milling, because down milling may be like this, here I am just showing that very schematic type of thing. Suppose this is job and this is cutter is moving like this. So, it is both are moving in the same direction. So, first you encounter a larger chunk of the material and then it goes. So, that is why in the beginning the chip thickness is more and after that it gradually drops to 0. In up milling, so therefore, because of this, down milling provides better surface finish and longer tool life. In up milling, chip thickness is 0 at the start, because in up milling, suppose you have the cutter like this and then it is going like this and it is like this here. Okay, that chip thickness is 0. So, that means this cutter, if it is rotating like this and then you have it is movement is like this, workpiece movement is like this. So, in the beginning it encounters this one flat surface 0 type and after that chip thickness keeps increasing. So, chip thickness is 0 at the start of the cut and increases to a maximum value at the end of the cut. Usually, you know that even in turning operation, finishing cuts are generally taken of a very small depth of this one and initially the cuts are high, but here you have got different type of situation. So, that is why this way may not give that much good surface finish. Now, up milling may be sometimes considered safer because it is there is a chance to be dragged into this one cutter. So, this is what happens that here in this case, let us see that some more advantages and disadvantages of this one. Suppose here you have got up milling and then there is a down milling here. Now, in the up milling, this is job is moving in this direction and cutter is moving like this. Let us say that cutter is stationary, so that table is actually relative motion is in this direction, relative to the cutter it is moving in this one. Okay. Or if the table is fixed, then naturally the cutter moves, but we are considering that suppose cutter is fixed at this location and this job is moving in this direction. So, you see that initially that cutter encounters this flat surface and as job is moving, it is getting more and more bite actually here. And in the down milling, it is moving in this direction, job is coming. So, initially it is getting a big chunk here, it has to cut that material and gradually it reduces. So, in the down milling, net force is directed downward. Let us see, this is down milling, B is down milling, and if we see that it is if you are seeing that job is moving like this and therefore, there will be one motion that it is cutting and that means cutting force on the job is going in this direction and at the same time there is a this one, that means it is the radial direction, there is a force like this and therefore, resultant is like this. So, resultant component is downward inside. So, it keeps the pressing the job against the table. So, therefore, it requires the simplified fixture. In this case, in up milling, what will happen that if we see that it is putting, so it is like this, you are having suppose you have force coming like this and then there is a that force, it is like this here, and then this will be okay. In the down milling also, suppose this is the force on this, and even if there is a radial force like this, so even then its component radial force direction can be shown like this. Okay. This one, let me show a first, because suppose it is cutting like this, so cutter is moving like this, so cutter is pressing because one component by tangential wise it is coming this way, and it is this way, and radially because there will be like this way. Okay. So, this is, so therefore, resultant is here. In this case it is like this, and radially suppose it is this, so that resultant is somewhat this. Okay. Now it is in this direction, cutter is moving like this. In this case cutter is moving in this direction. Okay. So, force each component is like this, and in this case the force component will be like this. It is having this way, and it is in more component is this direction. So, it is more inclined towards that resultant is actually towards this. So, it has a tendency to lift it up. So, that is why it requires strong fixture here. So, down milling requires simplified fixtures. It requires less power in feed motion, as the horizontal component of the net cutting force assist in the feed motion. See, job itself has a tendency to drag it, and it is going in that direction. So, less power is required. Cutting operation is smoother, as the tooth starts from maximum thickness and uncut chip thickness keeps reducing till the tooth leaves the machined surface at 0 uncut chip thickness. So, it is a smooth variation of the forces. Due to smoother operation, the process has a less tendency to chatter or undergo self-excited vibrations. So, these are the advantages. In up milling, when the cutter starts from 0 thickness like here, it rubs with the workpiece for some times, because here there is hardly any depth of cut. It is just rubbing, and for sometimes before biting into the material. So, this rubbing action reduces the tool life. This disadvantage is not present in down milling, although if the surface is sandy or scaly, then down milling may reduce the tool life than up milling, because here if it is sandy, suppose there is a sandy surface, sand is there, so initially this surface will come in contact, whereas in the down here even if there is a sandy surface, but we are cutting from this which is machined surface, so it will go and it will by this time it will reduce the big chunk. So, that problem is not there. So, tool life in sandy surface will be less in down milling, but otherwise in general the down milling will provide more life. So, but in spite of all the advantages of the down milling, it is not used in a machine with a backless eliminator in the lead screw nut drive of the table, because there is generally a backless. That is why up milling is always preferred in favor of the down milling, because without this the table has tendency to encounter jerky motion whenever there is a fluctuation in the cutting force. Let me tell you what is the backless type thing. I am showing in a very schematic way, simplified way. Suppose this is a lead screw teeth, these are the gaps, and this is corresponding nut portion. So, you know that nut thread will engage with the screw thread like this it may be. Usually there is always a gap between them. Ideally, thickness of this gap in screw will be equal to the thickness of the teeth of thread of this one nut, but usually that cannot be done, because if you make very precise, then it may jam and it will not have free movement, and due to thermal expansion also we need some space. So, we deliberately provide some gap between them backlash. So, that is not a problem. Assume that the nut is forcing the screw and it is just moving like this. So, suppose contact is like this, okay. But then suppose suddenly you reverse the direction, in that you have to move this much distance, that is called lost motion. So, that means whenever there will be reversal, then that type of problem will be there. So, that is called backlash phenomena. So, for backlash elimination sometimes people use a double nut compensation type of thing. That means suppose you have this type of screw and so many teeth are there, I am not showing them all, but suppose there is I put one nut in which the teeth are aligned in this direction, okay. Gap is still there, but suppose it is like this, it is like this, and I provide here another suppose nut. There are so many means nut threads, but I am just showing one. But in this I align in this direction. I can align in between two nuts, I can put special, so that this portion keeps pressing in this direction and other portion keeps pressing in the different direction. So, then even if there is a reversal of direction, you can see there is no lost motion, because this nut is already in contact with the screw. So, we say one nut is compensating for the other and it is called double nut compensation. So, in most of the machines there is no proper backlash elimination arrangement, that is why generally up milling is preferred there, and so that this can be, this phenomena is not there, and down milling is not preferred, because in up milling that this will always have it will always keep pressing in one particular direction, because these motions are in opposite direction. So, proper pressing is there. In the down milling that type of pressing is not there, okay. So, these are the reason. Now, in face milling the cutter axis is vertical or perpendicular to the work surface, and cutting is performed by cutting edge on the periphery and the face of the cutter. So, that is the face of the cutter also cuts, periphery also cuts, and we are doing here the vertical milling, that type of thing has been shown here. Now, let us discuss in the case of plane milling, let us say it is a horizontal milling, I want to see how the chip thickness varies. So, here I am showing that type of situation, that this is a cutter and let us say this is a table with a velocity workpiece velocity like this, and this is moving in this direction. So, naturally this is the case for up milling, okay, because the cutter is rotating like this and the job is coming like this. But let us assume that center of the cutter is here and this is actually coming here relative to the workpiece. Let us say workpiece is stationary, so it will naturally come here. So, initially it was at O and it was like this, and after that it has become like this here. So, it is rotating. Now, just see that here, if you just take it, if it is rotating in this position, it at O with O as a center, it would have covered this type of a circle of radius d by 2. D is the cutter diameter and small d is the depth of cut. But by that time it has moved at O prime, and suppose it rotates here. So, it will give like this type of thing it will give, okay. That means this is the center, okay. So, naturally if we assume that it was at position O and then we have kept it at suddenly at O prime, then in that case this will be the path. So, in a way I am saying that this much is the basically depth of that thickness basically. this is the thickness, chip thickness, because this portion of material will be removed, because initially itself at this location it is made like this, but then suddenly I will be moving and I will be putting this teeth here. Okay. So, that means because by the time that tooth, this was the tooth, and in this suppose we assume that this is this distance O prime is the basically feed per teeth. Okay. So, that means per tooth feed is this, and you have got this type of material. So, this D is the cutter diameter. So, D by 2 is the radius, L is the chip length. That means, we take the chordal length from triangles OBC and ABC. So, OBC this one and AB and ABC. ABC is this. Okay. So, that means this is so this will be the chip length actually, this AC. Okay. So, now here T is the T bar is the mean chip thickness, average chip thickness, B is the chip width. Chip width is actually not shown here, perpendicular to the paper, and tau is the time taken for material removed from the workpiece, V is the table speed, N is the RPM of the cutter, small n is the number of teeth of the cutter, and Tm is the maximum undeformed chip thickness, that is Tm, which is visible here. That Tm is this one, because it is going, and when it has moved like this, so next chunk is removed in this way, and it is Tm. So, Tm is this much. Now, let us see chip length from triangle OBC and ABS can be given as, suppose this is L square, that means suppose we say AC square. So, that is D by 2 square, because it is that diagonal is D by 2 square, and this minus this thing. Suppose I say D by 2, and this distance is actually D by 2 minus D. OB is actually OB, that means this distance is actually D by 2 minus D. So, if I want to find out this distance, that means BC from here to here, that means this one, let me show in a thicker way this one. So, I have to subtract from D by 2 square by Pythagoras theorem D by 2 square minus D by 2 minus D square. That is what is written here, D by 2 square minus D by 2 minus D square. So, by Pythagoras theorem this has come BC, and this is already written as D. So, this distance. So, now this square plus this square BA square will give me this square. So, that is why I am adding plus D square. Now, we simplify this D by 4 square and all those type of things, but assume that D is very small, so that D square can be neglected. Okay. Now, here also let me just see that it becomes D by 4 square, and this becomes minus again D by 4 square. Okay, okay. So, this becomes minus becomes plus dd, and plus it becomes d square minus d square, and that was minus d square, but this d square, this square cancels. So, this cancels. So, ultimately you are left with dd. So, L is under root dd. Why we say under root dd approximate only? Because this is really not perfect triangle, because this is curved surface, but we are assuming that it is more or less like a straight line. So, L has come under root d by d, square root of that. Okay, square root of d times small d times d. So, that means chip length will increase if the cutter diameter increases and also the depth of cut increases. Now, volume of an individual chip is actually L and average thickness T B. So, that means we can say T B under root d by d. Now, volume of an undeformed chip can also be obtained by dividing the material removed from the workpiece in time tau by the number of chips. So, volume of a particular chip can also come by this formula. V means speed of that table, B is the width and D is the depth and multiplied by time, and this is the total material removed in time tau, but by that time cutter has rotated by, suppose in 1 unit time it rotates by capital N. So, in time tau it will rotate by n times tau, and there are n teeths in this one. So, total number of teeths involved will be n this one. So, per teeth removal of the material is this. Each teeth is removing one, and I am assuming that each teeth is making one chip. So, that is what we are getting volume of the chip by this formula also. So, we can equate this and this, we can equate these two together, and then by equating 2 and 3, the mean undeformed chip thickness is given by this. So, we are getting T is equal to this one. Now, we can also say approximate the chip thickness by a triangle. Chip section is shown here, that can be like a triangle. So, therefore, we can say in the triangle if the average is this, therefore, Tm is equal to approximately 2T times. Okay, so, that type of expression has come. This expression is showing that the chip thickness will increase if the depth of cut is increased, but if the cutter diameter increases, then the chip thickness will decrease, and this is what will be like this, and it is and of course, chip thickness will be reduced if the number of teeth are more, okay, and RPM is more, and naturally if the velocity is more, table velocity is more, then the chip thickness will be this one. This is table velocity, that means table feed, and this is naturally that this is a table feed, and this will be N means this is RPM of cutter or revolution per minute. You have to use consistent units of course, no? That whether it is if it is in millimeter per minute, then you can use RPM, otherwise RPS can be used. So, another way of looking it like this, that suppose this is the upmilling process and this was in one position, then finally it is coming like this, and this is FT. I am showing that this is this, that means per tooth this is the feed. So, and it has come like this type of thing. So, we show here that if we show like that FT, so we show that suppose here it is this position, this portion I show in an enlarged way, and this is the angle psi here, and this one is angle psi. So, this angle is also psi, and this is T, and these are 90-degree we assume, and this is FT. So, from this also we can get some expression. Okay. So, that way we can see that basically we get FT sin phi type of thing. Now, here chip formation in the plane milling is like this. Suppose we want to apply the orthogonal cutting theory, we can consider it as a one cutting tool. One tooth means one cutting tool, and this is radial angle is this, that is rake angle. Radial rake angle is given here. This is radial clearance, and this is the chip, and this is Tm, this is S, and the chip is going like this. Now, chip thickness varies from 0 to Tm and may be approximated to uniformly this one approximated by this one, as we have mentioned there. Now undeformed chip thickness in face milling will go like this. In face milling, suppose this is in position O, and then suppose it has come in the position O prime, that center. So that means that if it has come in this position O prime, in that case this one is the material removed. So this is the maximum Tm. Okay, this is maximum Tm, and this is B prime, and this is what? This one. So in symmetric face milling, as the tool passes over the workpiece, the chip thickness increases to maximum value and then decreases. Okay, so tool is passing over the chip thickness. So now what happens, that here referring to this figure, the chip length is L is equal to arc of AB, that is the chip length. Now here chip length is actually dx, d is the diameter and x is the total included angle here, and 2b is the width of the workpiece, d is the cutter diameter. Then cos x can be written as 1 minus b by d square and 1 by 2. So expanding both sides of the equations and neglecting higher order terms, we get 1 minus x square this much. So ultimately we get expression for x as this much, b by d 1 plus b by 2d square, this one, and L is equal to b 1 plus b by 2d square, and this is this one. So that means this is the length of the chip. Okay, if that one this one, okay, that this has come length of the chip. If the, of course, if the diameter is very large, then b by 2d term, this term will become almost 0, and in that case you will get 1 plus. So that means length will be b itself. But if the otherwise, length of the chip is slightly more because of the curvature effect. So that means b by 2. So that means you have got one expression for that one. And volume of an individual chip, volume of the chip is equal to T dB. So it is that means length is known. Now I am multiplying length by that basically the average chip thickness and the corresponding that small d is the that means okay, that means depth in that direction. Okay, that means that axial depth. So we get T dB 1 plus, and dividing the material removal from the workpiece in time tau by the number of chips, like in the previous case, we get volume of chip is equal to V dB tau, but in that much time these many tooths have participated. So that means n tau, and that is why it becomes V dB divided by n. Now the average and deformed chip thickness is given by like this, both the volumes will be equated, and you will get undeformed chip thickness as T is equal to V divided by n and 1 plus b by 2d, and this will be square root of that. And in this case also we get similar type of expression, and expanding and neglecting the higher order terms, we can write T is equal to V by n 1 minus 1 by 2b by 2d square. So that means if the width increases, then the thickness decreases, because this is minus term here. So in milling operations, the undeformed chip size or the size of cut taken by an individual tooth is of prime importance, and not the table speed V or depth of cut D. The size of cut, however, depends on the various cutting parameter. Okay. So tool angles in face milling cutters are similar to turning tools, but the nomenclature are different. These angles are shown in next slide. Okay. When the helix or helix rake angle is 0, orthogonal conditions can be approximated by taking projections of mean chip thickness, and radial rake angle on a plane perpendicular to the cutting edge. So, that means it is when the side cutting edge angle is 0, alpha is equal to the radial rake angle. So, here we are showing the nomenclature. This is the cutter, and if we take one section at x6, this is coming like this. So, we get a radial rake angle here, we get a radial clearance angle here, and we are getting that alpha, and we are getting axial rake or helix angle. Axial rake is basically helix angle, and this is the face clearance angle, like that. So, that way we can make. Now, let us discuss about forces. We are seeing that there are some forces acting. Okay. So, these are will be denoted like a force acting along the tangential direction, then force acting along the radial direction, then force acting along the axial direction, and these components along longitudinal, vertical and transverse directions can be taken as FP, FQ and FR. When a straight cutter is used, the axial or transverse component is 0 and a two-dimensional force system is obtained, but we can use helical one also. So, you have to get another component. So, milling, due to periodic nature of chip formation, the forces also vary periodically, leading to variations in cutting speed and vibration. Now, I am showing the forces here. You are seeing that this is Fp prime, then Fq prime, and this is Fr prime in their perpendicular direction, and in this simple system that this is Fp, Fq and Fr horizontal, and this one with reference to table. And I am showing that one, if in a plane milling, in the straight cut milling, there is this one Fp prime, Fq prime, and this is going like that. So, these forces are shown on the this one. Suppose this tool is there, and this one is this is coming. So, actually this cutter is applying a force in this direction on the workpiece. So, workpiece is applying a force on the cutter in this direction, that means Fp prime. Similarly, the workpiece is applying a force Fq prime on the cutter in this direction, that means it is trying to lift the cutter and cutter is trying to press it down. So, Fq prime. So, these are the forces on the cutter by the workpiece. By Newton's law, it will be equal and opposite situation for the workpiece. So, that is why you are getting like this, and in this case there is a force Fp, again Fq, that means workpiece is putting a force Fq here, and also because this workpiece is actually dragging, okay, this one, yeah. So, this is Fp, Fq, and yeah, in the same way it has been shown, and this is okay. So, this is about this one. So, if it is in the opposite direction, then it should have been like this. Okay, that means it should be down milling situation. In that case, this will be this one. Okay, so this will be this direction will be shown in the opposite that direction then. Okay, so these are the force components. The variation of forces with motion of cutter in three cases are shown. Now, what may happen that suppose teeth are spaced very far away. So, spacing is far away, that means T is 2 pi by n is this much, but the distance, but this bite angle is only phi. So, that means one teeth has gone here, but the other has yet not come. So, in that case you will get this situation. That means it is the fluctuation is happening, spacing between teeth on the cutter is greater than the chip length. So that means force increases gradually as the chip thickness increases from 0 to maximum, but then it decreases suddenly. Then there is a gap because no contact is there, then it goes, and this is the thing. So this is a very jerky situation, you get that type of thing. Other situation is that psi is equal to exactly 2 pi by n. So force decreases and then suddenly it increases. The third situation is that psi is greater than 2 pi by n. In that case, what happens that here individual pulses are going like this and force is going up, but suddenly the other teeth also has made contact. So that thing is also there. So what happens that their resultant effect will be like this. So it is never becoming 0 and there is a less amount of fluctuation and you get that type of thing. So this is what we have shown. Individual forces have been superimposed. So first case, the spacing between teeth and the cutter is greater than the chip length, and second case is the spacing between teeth and the cutter is equal to the chip length, and the third case the spacing between teeth and the cutter is less than the chip length. These figures have been obtained by appropriately superimposing the individual pulses. Force fluctuations can be reduced by increasing the number of teeth on the cutter, but there is a limit since sufficient spacing must be available between two teeth, otherwise there will be lot of problems, including the chips may also get obstructed between. So reduction in force fluctuation can be achieved by using helical cutters which have several teeth remain in contact with the workpiece during cutting, because there is a helical. So in the width direction one portion is cutting, but the other is not cutting, like that. So it balances. Further, the contact between workpiece and the cutter in this case starts and ends gradually, leading to reduction in shock. When the helix angle is 0, the cutting force increases to a maximum value and rapidly drops to 0, as we have shown in this figure, that means here like that. But otherwise, if we superimpose individual pulses, then resultant force may be like this. So effect of helix is there to smoothen that force is coming on that one. In the face milling operation, the force components Fp, Fq and Fr are longitudinal, vertical and transverse direction forces. These force components can be measured with the help of a 3-component workpiece dynamometer. Transverse component Fr is usually small and it depends upon the width of the workpiece. Okay. So this becomes like this. Initial shock is reduced by providing cutting edge angle as on turning tools. When the helix or axial rake angle is 0, the forces can be estimated using orthogonal model. Force fluctuation occurs because of intermittent contact with the workpiece and the variable chip thickness. Also, the force pulses increases rapidly to a maximum value and drops to 0 on disengagement with the workpiece. Force fluctuation can be reduced by increasing the number of teeth in contact with the workpiece during cutting. Now, let us discuss something about the surface finish. Now, surface roughness in plane milling can be evaluated from figure this one. Here what happens, it is found that superimposed waviness occurs for each revolution of the cutter, but suppose this distance is S is equal to V by Nn. S is the feet per unit tooth, okay, that which we wrote Ft there. So it is V divided by N. N is the suppose revolution by that much time, and then what happens that here, that is denoted by S. Here that what happens, this is V is the suppose the distance of the table in meter per minute. If I divide it by N, I will be getting meter per this distance moved in one revolution, but if I divide it by N also, then I will get distance moved by 1 teeth. Okay. So, that means one portion was here and the other is here. So, here that is it is showing that suppose you have removed the material like this, and then we also moved, we move, this portion is here, then this has moved here. So, here it has removed suppose this much material. So, this much portion remains. So, this h is called basically the height of the peak. So, this can be obtained like that, d by 2 square minus d by 2 is this radius minus d by 2 h square s by 2. So, suppose s by 2 because this distance is actually s by 2. So, situation is like this is s by 2, s is here and this is h, this distance is h, this distance is h and this is really d by, this is this one. So, it is actually d by 2 minus h. Okay. So, d by 2 and this is h. So, if I do Pythagoras theorem, this is s by 2 square is equal to d by 2 square, this minus d by 2 minus h square. So, if we do simplify it here, this becomes from this one, it becomes like this, and simplification we get, we can put the expression for s and we get h is equal to v square by 4 d n square by n square. So, that means that your roughness height will be proportional to square of v, that means stable feed is more, then you will get poor surface finish, but if diameter is increased it is better, if more teeth are there better, if more RPM is there it is better. So, ideal surface roughness in face milling can be obtained from feed marks left behind cutter teeth. General approach for evaluating h is similar to turning, since the geometry of the face milling cutter tooth is similar to that of turning. Approximating the path followed by an individual tooth to be an arc of a circle having radius equal to that of the cutter, the feed mark can be drawn as shown in this figure 12. So, here also suppose we have this one sharp edge, in plane milling, face milling we are cutting like this and here it is h. So, like in turning, h is equal to s divided by tan gamma s plus cot gamma e. S is the feet per tooth and gamma is the end cutting edge angle and gamma s is the side cutting edge angle. And in drilling is the most common hole making operation and is performed using twist drill. The cutting tool is fed in the direction parallel to its axis of rotation. It is axis of rotation is this. So, the feed will be also in this direction. In drilling, cutting occurs on the straight cutting edges, cutting those are called cutting lips, and chisel edge here and the cutting edge is straight here. The chip formation occurs mainly at the cutting edges and the action at the chisel edge is one of pushing into the material like a wedge. So, chip generated at the cutting edges move up the axis of the drill along the fluid. So, it is chips actually move through the fluids due to helical that path and it is like that. So, drilling, when the drill is fed downwards with feed F, each of the two lips removed layer equal to F by 2 as shown in figure this one figure 14, that means there are two lips. So, each shares F by 2 F by 2. Okay. Now, here alpha n is normal rake angle. So, alpha n is shown here that if we take a section, so we can get here alpha n, section AA will give you alpha n, and alpha angle alpha n varies with distance RA and should therefore be defined with reference to the radial location on the section and can be evaluated approximately from this. there is a formula that tan alpha n is equal to Ra tan psi d by 2 sin beta by 2. Beta is the point angle and psi is the helix angle, d is the twisted diameter. Okay. Beta is actually complete point angle, that is shown here. So, this formula is there, and this one helix angle varies along the length of the cutting edge, but its value psi is usually defined at the periphery, at the middle of the cutting edge, that is at Ra is equal to d by 4, the normal arc angle becomes alpha n is equal to tan inverse tan psi divided by 2 sin beta by 2. Okay. So, alpha n expression has come like this. Cutting speed and other parameters vary considerably along the cutting edge, because here the cutting surface is different, here the periphery is different. So, making the chip formation process very complex. It is essentially an oblique cutting, and you are seeing here in this figure that n is there and f is there. This is point angle, two lips are like that cutting, and this is a point angle, and this one will be, that is a psi, and then this is alpha n, and then this is a section at AA has been shown here, and this will be psi, and this is okay, this angle, this thickness, chip thickness is shown here like T. Now, undeformed chip thickness from this figure is called T, chip width is B. So, this chip width is B, so T and B can be evaluated as T is equal to f by 2 sin beta by 2 and B is equal to d by 2 sin by beta by 2, similar to turning. So, these expressions are here given here. So, you are seeing that T is equal to B by 2, this one, so feed, and B is equal to this much, B is actually this bit here. So, B by 2, B is equal to d by 2 sin beta by 2. So, that means this is the, you can say this is the chip width. Now, forces and power. The dealing force can be resolved into the components. Fp is equal to tangential component, okay, and Fq prime is equal to force component normal to the cutting edge. Fq prime can be further resolved into two components. Radial component is Fr and thrust component is Fq. These components have been shown, these forces are shown here. Total force in the tangential direction during drilling consists of tangential components at the cutting edges and the forces due to frank friction. Chisel edge also contributes to it. Thus, for a twist drill with two lips, Fp is equal to 2Fp plus Fp1 plus Fp2. So, here Fp is equal to this one, okay. No, this will be Fp1 is this one twist, thus for a twist drill with two loops, that is one is due to chisel, okay, maybe Fc plus Fp1 plus Fp2. So, here hence Fp, these are Fp1 and Fp2 are the tangential components of the forces due to friction and extrusion at the chisel edge. Similarly, the total thrust force Fq in a dealing with a twist drill having two lips is given by 2Fq plus Fq1 plus Fq2, where Fq1 are the thrust force due to friction and extrusion and one is about the cutting. So, Fp1 and Fp2 are much smaller than Fp with more than 85% of the torque cutting from cutting action at the lips. So, this, okay, if I can use, okay, this is capital P, this is correct symbol, then I can use Fp, that means this is cutting component and this is Fp1 and Fp2, that means friction and extrusion. So, contribution are, so Fp is more than 85% and this is a contribution of force due to friction and total thrust is negligibly small, usually less than 3%, and empirical relations based on experimental results are of the form Fp is equal to C1 F to the power something, and Fq is the corresponding thrust component. We get this one. So, for mild steel, the value of exponents are generally around 0.8, and D means this is 2. Okay. So, D is that is diameter here, that is 2, and this is this one is 8.8 and 1. Now, surface finish drilling operations are usually considered as roughing operation. So, drilling operation is not much concerned with the quality of surface finish. For better accuracy, the drilling operation is usually followed by reaming. Okay. So, this is I am showing that one complete drill, that you can just see that actually maybe you take a real drill in your college and you can compare this one. This portion is called shank, which fits in a shank holder. Then these are the flutes on which chips will move, and this is inclined. So, this is helix angle, these flutes are inclined, and this is the drill axis. Then this is drill diameter, and this portion is called tip. Here you are having the cutting lips, and if we show that these are one cutting lip here, and then this is another cutting lip here, this is point. So, this is called point angle, and this portion is the flank, because cutting edge is there, then side surface is the flank, and here that this portion that body will be little bit down compared to the cutting lips. So, this is called some margin, this is cutting lip, this is going up to this, and this is called margin, and this is called, this is chisel. So, this is called chisel edge angle from here to here, and this is the flank, and this is called here basically the web thickness in this portion. Here it is this one, and then this is called fluid. Okay. So, that means this is the complete nomenclature of this one drilling, and a drill, and this has been shown. So, we have talked today about milling and drilling operation. Although the force calculation etc. is very complicated here, but we have actually discussed a bit, because these are essentially oblique cutting, but this will certainly give you some idea about the physics of the process. So, we will continue our discussion in the next class.